I knew you would say that. When you would ask me, because you really knew. I think you can, sort of, start reading people's mind. I'm just kidding. What are you?
Welcome everybody. I think we should start the morning session. We kick off with Durrer talking to us about testing cold dark matter.
Great, thanks very much, Roy. So it's a great pleasure to be here. And I want to thank the organizers for inviting me to give this presentation, which is actually mostly going to be a review, because I haven't worked directly on this topic for about a decade now, and maybe by the end you might see why. But the thing I'm going to discuss today is essentially how we can possibly constrain the nature of dark matter using observations of galaxies on small scales. And so obviously the core question here is, what is the nature of dark matter? We have a paradigm right now that essentially dark matter with most available observations works well if it's cold, purely cold and collisionist. So it has essentially no interaction either with itself or and it has no thermal interaction either. And it works exceptionally well, as you well know. And there's just a illustration of this. The illustration of this is that, of course, you can combine many different observations across many different scales, from the Lyman alpha forest at very small scales, galaxy clustering, cluster abundances, cosmic microwave background, and the lambda CDM paradigm fits extraordinarily well. However, once you get to scales of about a kiloparsec or so, or in that less than galaxy-sized scales, there are some interesting discrepancies, and that's sort of best illustrated by simply looking at a rotation curve of a galaxy. This is kind of how the whole area started. So if you look at rotation curves, particularly of dark matter-dominated dwarfs, such as this example here from Badaman, you'll see that the rotation curves are rather slowly rising. Okay? And of course, the rotation curve is a measure of the enclosed mass at any radius, in sort of a simple interpretation of it. And this is sort of the standard cold dark matter prediction, which is a density profile that has a cusp in the middle. That cusp scales as r to the -1. This is known as the NFW profile. And trying to fit the NFW profile to this data is very difficult. So this is sort of a best fit type model. And what you notice is that the NFW profile tends to rise very quickly in the middle. This tells you that there is, in the simulated expected profile of cold dark matter, you expect that the baryon, or the matter rather, is much more concentrated in the center than you actually observe. So for instance, you can contrast that with an isothermal model, which has a flat pool. And in that case, you can actually obtain a very good fit. So these dark matter density profiles were the first hint that the standard cold dark matter paradigm perhaps breaks down on small scales. There are other problems as well, which may have related solutions. Another one is the missing satellite problem. We'll talk more about that one. And more recently, this has morphed into what's now called the too big to fail problem, which also we'll talk about. And this has spurred a number of different solutions, particularly in the dark sector. So in other words, taking the assumptions of cold and collisionless and relaxing those assumptions, either making it warm or making it interacting. In fact, there's a huge number of other ones that I won't discuss in full detail. All kinds of funny names like fuzzy dark matter and all these sorts of things, bosons, not condensates. I'll focus basically in this talk on whether dark matter is perhaps warm and whether it has some interaction cross-section. But the other thing I wanted to also discuss is the importance of baryonic physics. Of course, these are the central regions of galaxies, and although these are so-called dark matter-dominated dwarfs, perhaps the impact of baryons can be significant even for the dark matter. Okay, so again, just to sort of recap what the latest situation is on the density profiles, this is, again, still not solved, I would say, in purely from a cold dark matter perspective. So as I mentioned, cold dark matter predicts cuspy profiles. In other words, if you take the density profile it scales as r to the alpha, that value of alpha that you measure from dark matter simulations ranges from sort of minus 1.5, which is the so-called Moore profile. Minus 1, it would be an NFW profile, and there's some hints that, if the central dark matter is sort of a fixed phase space density, then it might be a little bit shallower. But in all these cases, it's quite cuspy. And so you can go out and measure in either dwarf galaxies, where you think your dark matter dominated into very low radii, or in clusters, where again, there's a very large dark matter component. And you can try to measure the slope of this profile. And so this is a compilation of a number of different data from O et al. That was reproduced in Ponson and Governado. And you see where all the data lie. Again, they lie much closer to the alpha of 0 line than they do the alpha of minus 1 line, which is the NFW prediction. And this is essentially the issue. It also occurs in clusters. To perhaps a varying degree. It's a little bit more difficult to do these measurements in clusters, but here's a compilation by Newman et al., and beta is just minus alpha in this case. And so you see that this is the NFW profile, and this is a compilation of various measurements with their uncertainties. And you see there's a systematic trend that the profiles are always much shallower than is predicted in CDM. So that's the first problem. Here's the missing satellite problem. Again, this was noted in the late 90s, that if you run a simulation, and this is very generic, it's just one I picked from Nick Ganadian, of a Milky Way sized halo or a cluster sized halo, they're pretty self-similar in the dark matter, you see that there's a very large number of little small halos dotting. This is sort of the virial radius roughly of the halo and of the Milky Way. And you see there's a huge number of little halos that, in sort of the standard approach, you would say that there should be galaxies associated, there should be stars collapsed within these halos. And when you go out and try to observe and figure out where those galaxies are, most of them are not there. So here's a picture of the local group, and the point being that these things all have names. I mean, there's a handful. There's maybe tens now of such local group galaxies. When CDM would predict many hundreds. So this is illustrated in this plot here by Ben Moore in sort of this seminal 1999 paper, where he plots up the cumulative number of halos as a function of the circular velocity scaled to that of the Milky Way. And this falls well short of the predictions from CDM. So the solid line and the dashed line here are predictions for clusters, for a cluster and a galaxy, very high resolution, even at the time at least. And you see they're pretty self-similar. In fact, what's interesting is in clusters we do find these halos, right? So this is data from clusters, right, from a galaxy cluster. So there's no missing satellite problem in the clusters, but once you get down to something like the Milky Way, there's a huge missing satellite problem. So what's going on there? Okay. So that's sort of the point here. Here we go. So the point is that CDM predicts hundreds of such subhalos. You observe tens. Well, as soon as this sort of data came out, or this sort of comparison came out, the theorists said, well, wait a minute. We know that a lot of these satellites should be dark. Why did we know that? Because reionization heats the universe to globally around 10 to the 4 Kelvin, right? This is just because the latent heat from reionization, the ionization potential of hydrogen is 13.6 eV. Then, if you have a few eV extra, you're going to heat the gas to 10 to the 4. So that temperature is then maintained until today, thanks to photoning from the AGN galaxies. So that's going to suppress galaxy formation at circular velocity. You can convert that temperature into a circular velocity just from equipartition arguments, and that circular velocity corresponds to about 30 to 40 kilometers per second, depending on your exact assumption. So what that means is that we should not expect these halos, even if they exist, we should not then expect them to be bright. We should not see stars in them. So maybe it's not surprising we don't find all these local group satellites. So all these things basically, that are the difference between the CDM prediction and the observations, maybe they're there, but they're bright. They're not lit up with stars. So, in fact, Kopasov et al. Went off and did a very deep search for more local group dwarf galaxies down to very faint surface brightnesses. And then they had some very simple toy models where they truncated the star formation within halos below a certain circular velocity with some various efficiency parameters. And in fact, they could get a pretty good fit to the observed data. So that seemed to be okay, right? Okay, so now we're not so bad. We can simply explain the numbers, the missing satellite problems with reionization. But there's another problem, okay? And this has come to be known as the too big to fail problem. So this this is essentially comes about because now we have both better simulations and also, as I'll show you, very interesting and better data. So if you look in very high resolution Milky Way sized dark matter simulation, so this is an example of one of these types of simulations, the Aquarius simulation in this case. This is sort of the size of the Milky Way disk down here. This is the Milky Way halo, out to about 200 kiloparsecs. You see it's littered with these tiny halos. So you're saying, okay, fine. Maybe all the small ones below 40 kilometers per second are not bright. That's great. However, when you start to look at the radius of these the observed Milky Way dwarf satellites versus their circular velocity, right? So now with HST, you can go out and actually measure the radii of these things. You can measure their circular velocity. What does that tell you? The circular velocity is telling you about enclosed mass. The radius is, obviously size. So those two things combine to form a density. So now you can measure the density of mass within the optically detected radius of these bright Milky Way satellites. And the range that you get is of densities sort of spans this range in radius and circular velocity. Well, when you go to, in this case, this is from the Aquarius simulations, what you notice is that the simulated halos all predict that you should be much denser in that central region. Okay, so these are sort of points from the simulation, picking out halos in the simulation, and particularly look above about 40 kilometers per second. You say, okay, maybe we should ignore everything below 40 kilometers per second because of reionization, but look above that, it's still way denser, right? In other words, the subhalos that you see in the simulations are way too dense to match any Milky Way satellite that's observed at those, at anything, basically. So this is the reason it's called too big to fail is basically these galaxies should be too big to fail. Yet we don't see anything like that in the data. Okay? This is sort of another way to present that idea by looking at putting it on essentially a rotation curve again. So this is circular velocity versus radius, and you can put individual galaxies on this point. You have some radius that you've measured their circular velocity, and then you can overlay on that the predicted rotation curves that you would expect for subhalos of various that you get from the Aquarius simulation. And sure enough, all of these things, you would expect these things to live in 24 kilometers per second or less halos, right? There are all these 40 kilometers per second halos lying around in the simulation that have no analog in the observed Milky Way dwarf regime. So where are all these things, right? This is the too big to fail problem. So again, both of these things are basically reflecting the density of dark matter in the central region, right? That's kind of the king. I'll very briefly mention MOND, but not go into too much detail, just sort of for completeness. You know, one theory for how to reconcile these things has been that actually the law of gravity is not 1 over r squared on large scales. It actually goes as 1 over r, and there's some characteristic acceleration scale which this transition occurs. And you can get pretty good matches to rotation curves, as Rob Swatters and many others have pointed out. However, it works for almost nothing else, or at least it works more naturally for almost nothing else. Certainly, bullet cluster, you need neutrinos and relativistic extension, all these things, and it becomes much more less natural than CDM. CMB, Lyman alpha force, it becomes very difficult to accommodate this in MOND. So I would say that this is sort of less favored in the community. It's still touted. I think most of the people who tout it are people who do observations of rotation curves. So more sort of to the point of this conference is people have been thinking a lot, and they continue to think about whether we can modify the properties of dark matter. So obviously, if you make the dark matter to have some temperature. Essentially, you have it's light enough such that it has a free streaming length that will wash out the cusps of these galaxies. So you have to get exactly the right mass in order for it to have the right free streaming length that will then remove the cusps of these galaxies. So there's a nice project called the MAGIC simulations, led by Andrea Maccio's group in Heidelberg. And so this compares a galaxy, a zoomed individual galaxy in CDM and warm dark matter. And it's a little maybe hard to see in the sliding, but there's a lot less structure here. The central part is less concentrated, right? They've removed a lot of these, it's a little hard to see with the light, but they've removed a lot of these little satellites that are here in the CDM case. So this serves sort of to work for both problems. It lowers the central density of dark matter by essentially puffing out the dark matter thermally, and also removes the number of satellites. Of course, it also has other effects, right? This is not the only thing that it's going to do, and particularly it of course truncates the power spectrum on small scales. You wash out all the perturbations on small scales. So when you have a power spectrum now, if you have CDM, it basically truncates depending on the mass of the dark matter particle. So if you have, this is labeled by the particle mass in keV. So this is the 5 keV particle, it's close to CDM, 2 keV, 1 keV. As the particle mass goes down, of course the free streaming length goes up, and it washes out more structure. The thing is this, again, as I mentioned in the beginning, right, we have very good measurements of the power spectrum on these scales, particularly from the Lyman alpha forest. So the first question you can ask is, what particle mass do we need in order to match sort of observations, right, of rotation curves, right? And so this is something that Herpich et al. Looked into. And so just focus on the solid lines here. That's the blue line is the CDM, and these are various warm dark matter models, and then they're subdivided into their components. But the point is that if you remember, sort of rotation curves were doing kind of like what the red line is doing, right? They were sort of very slowly rising. Maybe for this mass galaxy, it's more like the green line, but it's certainly not like the blue line. You very rarely see this sort of peak, particularly on these dwarf galaxy scales. So what that tells you is that you need at least 2 keV, maybe maybe even 1 keV to really sort of make a significant impact on the dark matter, on the core density of dark matter. Again, that power spectrum alteration has implications for other things. So here's the Lyman alpha forest, which you can look at high redshift. Again, this is a line of sight to a distant bright object like a quasar, where you take a spectrum, and this is all neutral hydrogen absorption. And these are predictions from these simulated cases for different values of warm dark matter. And the green line's a little hard to see. That's the original CDM case. But the thing I want you to notice is that as you go to the blue and black, this sort of washes out the structure, right? You're sort of making the peaks less peaky. That's what essentially this thermalization does, is free streaming. Well, alignment alpha forest, I want to point out, is very simple physics. Hopefully most of you are familiar with it. It's one of the pillars now of modern cosmology. We really understand it extremely well. So when we make modifications like this, we can really test that against data. So this is something that actually I worked on with a postdoc at Princeton, Narayana et al. In 2001, and at that time the data was good enough to say that the mass of the dark matter particle had to be greater than about 3/4 of a keV. Okay? So that would still be okay. However, of course, the data has gotten a heck of a lot better since then. And this is a recent work from Matteo Biela's group, and particularly going to high redshift and small scales allows you to really probe the differences between dark matter or cold dark matter and warm dark matter. And you see that this is a 2.5 keV warm dark matter simulation, power spectrum of alignment alpha forest, and here it's clearly very discrepant. Okay? And from this, they argued that their 1 sigma fit was about 8 keV, above, mass above 8 keV. Their 2 sigma fit is about mass about 3.3 keV, and their best fit is essentially cold. So if this is to be taken seriously, and I think it is, then this really sort of excludes warm dark matter from simultaneously solving these small-scale CDM problems. Okay, well, what are some other ideas? What about self-interacting dark matter? So you can say that dark matter interacts with itself with some cross-section, and that will, of course, thermalize the core and wash it out, right? And this is something I worked on back in the day with Dave Spergel. And indeed, we can find that when we do simulations of dwarf galaxy-sized halos, the solid line here is the CDM prediction, and then this is several cross-sections per unit mass that we chose to test out, and sure enough, we could definitely flatten the central dark matter profile. Okay, so the kind of numbers that we needed was something like between 1 and 10 centimeters squared per gram. And indeed, when you look at the inner slope, right, this is the original CDM case, the solid line. This is the original CDM case of the solid line, and if you go down to modest cross section, you can already start to impact the central profiles quite a lot, and then quite an extreme cross section, you can get it down to sort of the observed range. Again, simulations have gotten a lot better, right? But there's also been other data that has really started to constrain this. So this is some more recent work by Rocha et al. And they looked again in a similar range, actually a little bit lower cross-section range. So the most extreme case is not that I considered was not represented here. This is sort of the less extreme case is the green one, the green one, no, the blue one, and then the lower cross-section, even down to 0.1, is the green one. And you can see it makes a little bit of difference, not much at the dwarf scales, but somewhere in between sort of 0.1, which is green, and 1, which is blue, can actually flatten the core reasonably well. So they argue that basically, well, maybe with something like 0.5, you'd still get a decent effect. However, we now have other constraints on the interaction cross-section, for instance, from the bullet cluster, because this gives I think it was mentioned yesterday, so I won't go into it too much, but nonetheless, the separation of the dark matter relative to the gas allows you to constrain how much interaction those two dark matter halos had when the clusters collided, and Randall et al. Argued that this limits the cross-section to less than about 0.7 centimeters squared per gram. So again, this is getting a little squeezed, right? I mean, we need this sort of cross-section for dwarf galaxies or higher, and this is the limit from the bullet cluster. One possible way around this is if the cross-section was somehow velocity dependent, because of course the typical velocities in dwarfs are much less than in clusters. So if it had an inverse velocity dependence, let's say, which many particle candidates have, then you might be able to reconcile these two. But it's certainly not the most straightforward thing. Okay, so meanwhile, across town, all the galaxy formation people have been working hard on trying to understand galaxies, right? And at first, people thought, oh, well, whatever. The baryons are just 1/6 of the mass. How can they do anything? right? They're not going to affect the dark matter, particularly if you have a dense core. How are you going to get rid of that with baryons? So it was pretty much ignored. There was a paper by Whaley Penn in the late 90s that argued for this, and everyone thought he was crazy. But, right, first of all, you have to recognize that baryons are not expected to be subdominant at 1 kiloparsecs, right? These things, baryons should, in a simple model, all collect down to the center and should be extremely dense. And within a kiloparsec or so where the problems are, you know, they might not be subdominant at all. You see that they're subdominant now, but you know, that's not necessarily means that they always were. They also produce a lot of energy, okay? And particularly in these dwarf galaxies from supernovae, from other feedback mechanisms. And this has been the new aspect of galaxy formation in the last 10 years that has really developed. And we have a better understanding of what sort of energetics are involved. And of course you have to notice that the rotation curves and all that are actually measured from the baryons. They're not actually measured from the dark matter, and non-circular motions and things can have an impact. I won't talk about that too much. So the question is, you know, have advances in sort of galaxy formation physics allowed us to understand, particularly using very sophisticated hydro simulations. This is just a movie from one of our simulations where you have inflows and outflows of material and all these sorts of things going on. Can these sorts of processes impact dark matter? So to very sort of briefly argue for why galaxy formation people have decided on very strong feedback, it's important to have a sort of intuitive picture of how galaxies form. And so here's sort of a simple cartoon model that we've been working on, which basically treats galaxies as sort of gas processing factories. So here's your galaxy right over here. It's like a little factory. What does it do? It converts gas into stars. Where does it get the gas? It gets the gas from the intergalactic medium, pulled in by gravity, right? Only some of it makes it down into the galaxy, into the, you know, for raw materials. So you're being fed by gravity, gravitational accretion, and then after that, basically, you have you know, some fraction of it going into stars and some fraction of it being ejected in an outflow. Okay, and the ratio of these things, the outflow rate compared to the star formation rate, is canonically referred to as the mass loading factor eta, and that so you see how that would divide up. And there's also some complications from some of that material also adding back in. Nonetheless, in this simple model, you can actually just write down what the star formation rate is as a function of these sort of parameters, eta, zeta, so on and so forth. Now, we don't know what these parameters are. They're very difficult to simulate directly. They're very difficult to constrain observationally. Nonetheless, we have a lot of observations of galaxies, and we can try to indirectly constrain some of these parameters by comparing to those observations. So this is the metallicity down here. I won't talk too much about that in this case. So we did this. We essentially put this very simple equation, almost a purely analytic model, right? Because we know the gravitational accretion rate. That's just set by dark matter. We can calculate that pretty accurately. So that's the input to this model, right? And then we have three parameters. We have these three parameters: the mass loading factor, the zeta parameter, which is sort of preventive feedback, and this recycling. And we can fit this to a whole bunch of data, okay? And amazingly, we can get a really good fit, okay, to some key scaling relations, things like stellar mass versus halo mass, mass metallicity relations, star formation rate, stellar mass. These are some of the most basic scaling relations that have been observed now out to redshift 2 for galaxies. And we can get a very good fit, you know, reduced chi-square about 1.6, and it's pretty good given all the systematic uncertainties. So, what does this tell you? One of the things that this tells you is what outflows, what mass loading factor do we need as a function of halo mass and redshift to actually get all this data right? And the point is that it's a very strong function of mass. So this is eta plotted versus stellar mass from our model, or halo mass from our model, okay? And what you notice is that it's an extremely steep relation, all right? And look at some of the numbers. So in a Milky Way dwarf type galaxy, 10 to the 10 solar masses, or below, right? We're expecting that the amount of outflow, the dense outflow rate is 100 times the star formation rate. It can be even higher, right? It's even higher at higher redshift. This is redshift 1, redshift 2. It can go up to 1,000, right? So when you say that these galaxies, these dwarf galaxies are dark matter dominated, well, yeah, because they've ejected 99.9% of their baryons. That's why they're dark matter dominated. And surely ejecting 99.9% of the baryons from the central region is going to have an impact on the kind of structure in the central region of these galaxies. I'll point out that the prevalence of this type of idea that there are these large, strong outflows in galaxies, particularly star-forming galaxies across cosmic time, was not invented to solve any of these dark matter problems. It was really designed to do other things, like enrich the intergalactic medium with metals, reduce the amount of baryons being converted into stars, which is a canonical problem. We have to get the mass-metallicity relation right. It's very helpful for making late-time disks, so on and so forth. So all these Hydra simulations now include, at some level, parameterized outflows, which can either be from the supernovae that are driven by overpressurization of the ISM, radiation pressure, so the young stars that are formed are pushing on the baryons from their UV photons, and of course stellar winds as well. So this is just one slide on galaxy formation. I won't talk any more about all these things, but the point is that all these very strong outflows are actually necessary in order to get galaxy formation right. Okay? Now we'll see what impact they might have on the dark matter. Okay? So indeed, they have a pretty big impact. So the group that's been looking into this the most is Fabio Governato's group, and so these are some results from his 2012 paper. And indeed, what you see is that if you plot so here's just density profiles now as a function of redshift. So the dot dash line here, this one that goes here, is the dark matter only simulation. So they run a comparison simulation that's dark matter only, and then they run with all their gas physics that drives these strong outflows and so on and so forth. And so this is the results at redshift 3, 2, 1, and 0. And you see it's really flat in the core. Right? This is the actual total mass density, right? This is not baryonic mass density, right? And in fact, when you compare it to the alphas, remember that inner slope profile parameter, right? Here's all the data from a recent H1 survey called Things, and here's all these simulations, the red points, okay? And in fact, you can see versus the dark matter, if you run a dark matter only simulation, they sort of all end up following what you expect from NFW. Essentially, that's that solid line, right? But with the baryons and with the outflows in particular, they end up much higher values, I guess, of alpha, higher negative values, so flatter slopes. So they have a very big impact. However, one thing that has been pointed out is they only have an impact above about this mass scale, 10 to the 6 or 10 to the 7 solar masses. Why is that? Because in these galaxies, there just hasn't been enough supernovae to actually drive these strong outflows and affect the mass profile. Okay. I won't go into this too much, but Ponson and Governato have had some very nice papers that explain it analytically as well how it is exactly that the baryons couple to the dark matter. And the thing that's sort of key is that you have to have these repeated, explosive events in the central regions. And what happens is that sort of unbinds the dark matter particle and ends up putting it on a higher orbit, on a larger orbit. And when you do this process repeatedly, you can really spread out the core. Again, this is because, although you're getting rid of all the gas, this is a large amount of gas, the large amount of the mass that you're getting rid of within a kiloparsec or within the core. Okay? So, so this group, and others as well, they're not the only ones, have argued that basically, baryonic feedback can basically solve this small scale problem. But there's been arguments against that, okay? In particular, they've said that this is a work from James Bullock's group, Shea Garrison Kimmel and company, and they noted that, look, let's start with a simple galaxy with a core. How much energy do you need to move that material out, and all in the dark matter in particular, out to the kind of radii that you need in a core? And what they notice is that coupling, if you look just in very small galaxies, local group dwarfs, these are things that are very small, even coupling 100% of the supernova energy directly to the dark matter through this mechanism still requires more supernovae that have gone off in this entire galaxy. Okay? So this is illustrated in this plot here. So if you just look at the right plot, what this is the mass of dark matter within 500 parsecs as a function of how much feedback they put in, how much of coupling they allow between the dark matter and the supernova energy. Very simple model, not cosmological or anything like that. The point is that you expect no more than maybe 10 to the 3 or at most 10 to the 4 supernovae to have been gone off, right? Because you see the stars, you can count them, and therefore you know how many supernovae. And the point is to get down to the kind of observed ranges of the dark matter mass within 500 parsec, you need huge amounts of numbers of supernovae, more than have been observed. Okay? So, now there are all kinds of problems with this. This idealized simulation began with the core already formed. In the hydro simulation, the core would build up. So you wouldn't have to get rid of all of it at once, right? You sort of never keep it from forming. And so the energetics become a lot easier if you don't just form a core in the first place, rather than try to get rid of a preformed one. But nonetheless, I think it's likely that the solution must have some other contribution besides supernovae, or we're getting the number of supernovae wrong, which is because of our IMF. So, and that's kind of scary. So, I just want to point out that the self-interacting dark matter, I got this slide last night from James Bullock. Self-interacting dark matter can also solve this too big to fail problem in the dwarfs, okay? And that's what's illustrated here. So again, what they've done is run several self-interacting dark matter solutions. Here's a CDM, this familiar problem that the dwarfs are expected, to have too high a velocity at the radius where you measure them, right? They're too dense. But including self-interacting dark matter, maybe between 5 and 1, would indeed solve this, okay? And this is a paper that's about to come out from Elbert et al. Again, one has to be mindful that there are other constraints on self-interacting dark matter cross-section that are right in that range and kind of limited. So, you have to maybe be careful with that. However, there's another effect that has been pointed out, that was pointed out by Zolotov et al., which is specific to local group dwarf satellites. In other words, the local group dwarfs that we see all are not just individual galaxies that are sitting out there in the void as isolated things. They're actually satellites of the Milky Way. And by being satellites, they're subject to other forces besides, just supernovae, so on and so forth, particularly tidal forces, right? In other words, you can tidally heat the central regions of these local group satellites. So what they did, what Zolotov did, is to go into simulations and pick out, within full hydro simulations, pick out Milky Way-sized galaxies, look at their satellites in particular, and study those, right? And what they found, so here's an example. So this is, again, the missing satellites problem here, just the number of satellites now plotted versus luminosity rather than circular velocity, but it's the sort of same thing. So here's their two simulations. They have, maybe a little bit shy of the full Milky Way halo mass, but in that range, right? And these are the number of satellites that they get below this particular luminosity limit, and they compare to M31 or the Milky Way, and sure enough, they're sort of in the right range. So these solve the missing satellite problem. Now, what about too big to fail? Can they also solve that? Well, what's interesting here is they looked at the circular velocity at infall of these satellites versus the circular velocity that they measure today, okay? And what they noticed is that this circular velocity is really much less. In other words, the circular velocity in this case, 1 kiloparsec, has gone much lower than what it started out when it first fell in, right? And so this sort of difference can really, this is a factor of sort of 2 to 3 lowering, maybe even 4, lowering of the circular velocity. So in other words, if these satellites were expected to come in at 40 or 50 kilometers per second, when you go to observe them, right, today, once they've been tidally heated, they will have circular velocities of like 15, 20, which is exactly what you observe, right? So in a sense, this is a way to solve too big to fail, and the baryons are crucial here. The dark matter has a small effect. These blue points are the dark matter only simulations. There's a small effect if you just consider the dark matter tidal heating. But in fact, the baryons are important for this because they again, explosively eject this material at the center and can really lower the circular velocity. So, again, that's basically, from my viewpoint, kind of the summary of the current situation. Certainly, it is true, I think we all agree in the community, that feedback lowers the core dark matter density at some level, right? How much, now, is the big question. It does more so in small galaxies, which is what you want, particularly because the outflow rates are much higher. The amount of material you have to get rid of is much larger. So if there are plausible models out there, as I've shown, that help both the cusp and the too big to fail model concurrently with the same mechanism. However, there's still questions about whether this will really work for the smallest local proof dwarfs. We didn't talk about clusters at all, right? What might happen there? These supernovae, aren't going to be very effective there. So there's maybe something else going on. And the energetics of this, I think, hasn't fully been solved, and how you couple that energy to both gas and the dark matter. I would say self-interacting dark matter is also viable, right? It's the cross sections that you need are things that are now starting to be ruled out by things like the bullet clusters, so that may be a little dicey. The other thing I want to point out is that not all central dwarf galaxy profiles are isothermal. There's a big range, right? So one of the problems with all these dark matter models, if you say that all the dark matter profiles should be cored, that's also wrong. There are definitely galaxies where it's not cored, where it looks more like NFW, right? So you have to produce a diversity of density profiles. Feedback is good for this because it's very stochastic. And of course, people I think have not looked at this very much. Does having these large interaction cross-sections have important effects in the early universe when the universe itself was very dense? Warm dark matter, I would say, is less promising, in particularly because the mass you need to do this basically can be ruled out by other constraints. Barely so, though. So maybe there's some play there. So essentially, my viewpoint is that we know this feedback and stuff has to happen. I mean, we see it from completely different perspectives. And until we can rule out that this stuff is not responsible for removing the cusps in the dark matter, I think, these are interesting, but not so well motivated. So that's the summary of why I haven't worked on this in the last few years. But I still think it's extremely interesting, and there are a lot of interesting challenges left yet. Thanks.
Any questions?
Just to start from your bottom line, no compelling reason for exotic dark matter. One dark matter we know exists are massive neutrinos. So we know they exist. They only upper limits from space, but it's very likely that the mathematical source will detect them. But for some reason, correct me if I'm wrong, simulations have kind of ignored them, except for, I think there are a few groups that...
There are a few groups, I think.
Could you comment on the state of the art of these and challenges in actually implementing the massive neutrinos?
Well, it is difficult because essentially you have to imbue these things with very large velocities at early times, and that really messes with your code. But I don't think that's actually the main issue. You can do it, and people are doing it. I think the issue is that just from the current bounds on delta m squared, the global contribution from neutrinos has to be pretty small. It has to be pretty subdominant to cold or whatever other dark matter, right? So from the perspective of the core and things like that, you might be able to reduce the strength of the core 10-20%, something like that. But that's not going to fundamentally change the kind of things that we've talked about. The rest of the cold, if it's cold or warm or whatever it is, it's still going to form a core, etc. So I agree, it's an interesting thing to look at, and maybe it could be a helpful thing along the way. But I don't think by itself it can solve the problem. That's at least my view.
There is a problem of the globular clusters, right? In that case, you have stars 10 to 4, 10 to 5 solar masses, and you don't have the dark halo. So can you get rid of the dark halo by tidal interaction with the galaxy?
Yeah, in general, that's thought to be the case. So it's unclear whether these globular clusters are very small galaxies that formed in the very early universe. At least the metal core globular clusters are sort of consistent with that idea. The other option is that they might, because they're much more prevalent around ellipticals, they might be formed in merger-type interactions. In which case, there's no reason to expect they would have formed with any dark matter in the first place. They're just large, giant molecular clouds that have happened to collapse that are of that size. So in that case, they would have never had any dark matter. And this is actually a much better fit to more of the metal-rich globular cluster population. So, so I think it is possible, and I think I'm not completely familiar with this, but I'm not terribly aware of any major constraints on dark matter by tidal removal, because these things are really small. But
let me try to understand better the Lyman alpha constraints on warm dark matter. If you have, I mean, let me just go a little bit beyond warm dark matter and assume you have some arbitrary suppression of power on small scales. Because warm dark matter is a very specific form, because it's just non-relativistic particles.
right.
Now, to what extent does Lyman alpha really test the scales where you would need a suppression? I mean, if you would have a cutoff that would be much sharper, let's say, would Lyman alpha still copy that? Or
that's a good question. I think you could play with that. I remember back in the day, we actually tried some simulations. Let me pull up that Lyman alpha force power spectrum. We tried some simulations with that exact idea, with basically truncating the power spectrum above some K. We weren't able to distinguish that between warm dark matter given the data, but it's a fair question to ask whether or not, if you were, here's the power spectrum data, right? It goes down to, these sorts of K values about 10 kilometers per second. The new data does, this one goes only. But, and it continues on the way that CDM expects. So basically, if you cut off power on any scales larger than that, I think you're going to see some effects in the Lyman alpha forest. I don't, quantitatively how much that is. But it's a very small scale, right? I mean, that corresponds to a scale of, 100 kiloparsecs or, maybe a few hundred kiloparsecs. So any time you suppress the scale, suppress power on scales above or below, smaller scales than that, then you might have problems.
yeah, but the typical range where you would really strongly need a suppression of power is kiloparsec.
No. So I mean, it's not. So again, those galaxies are collecting material from much larger scales, right? So the kiloparsec scale problem is actually reflective of an initial density perturbation that's on much larger scales.
Okay, I think it's time to move on, given the time. Thanks very much again, Maria. Our next speaker is Ruth Durrer, who will tell us about large-scale structure, angular power spectrum and bicycle.
Good morning, everybody. Can you hear me?
Yeah.
concentrate especially on the angular power spectrum and bispectrum, and I will also motivate why I think these are interesting topics and which we should. I will give a brief introduction and then tell you a little bit again what Tommy has already talked about yesterday, what large galaxy surveys really measure. Then I will introduce and discuss a little bit the angular power spectrum and the correlation function. And I will show a couple of applications of it in real experiments. I will concentrate on major nuclei and say what was to do with it, for example, use it for an Alpha-Kaczynski test. And then I will come to second order and the bispectrum. There I will only have preliminary results. This is still very much work in progress. As you all know, we are all fascinated by the CFD and by the amazingly accurate data and theory we have about it. And we would now like to repeat kind of this success story of cosmology, which has helped us to go from order of magnitude knowledge about cosmological parameters to percentage determination. We would like to repeat something like that with large-scale structure. Here we have already run big observations of large-scale structure. This is the long Michigan Sky Survey. And can we do something similar like we have done with the CMP with this data? There are advantages. One obvious advantage is that the galaxy distribution is a three-dimensional data set. So we have much more modes at our disposition. In the CMB we have a couple thousand modes. In the large-scale structure we have 1 million modes. Let's say if we can go down to 10 megaparsec scales. It has disadvantages. It's a much more complicated data set. Here we don't only see tiny fluctuations. We see fully formed galaxies. We see the light. We don't see the matter directly, etc. There are many complications. And we also know that the matter fluctuations are large on small scales. So we have fluctuations are not always small. In the mildly nonlinear regime, I will advocate that might even be an advantage. We have more data. We have not only the power spectrum, which contains all the statistical information on a Gaussian data set, but we have relatively considerable higher statistics like the mass spectrum, from which we can learn a lot of new information. So far, what people have done mainly, they have looked at the power spectrum in Fourier space of the large-scale structure distribution. Here this is power spectrum called Anderson et al. From the Voss data. And the most interesting feature here are these acoustic peaks, which are the variable acoustic peaks, which are the same, kind of the same peaks which we see also in the CMP. They are from an epoch which is a little bit later, and the scale is not quite the same, but they are the same basic feature that we see in the CMP and which we have been using to learn so much from the CMP. But now we are looking at large-scale structure all through the universe, and not only on small scales. And we have to take into account that whatever we see is on our pulse light column. We only see two spatial transverse direction and light direction. We have to take that into account when we want to analyze a galaxy catalog. Also, we measure, what we actually measure is redshifts and angles, and the redshifts are perturbed by peculiar velocities and also by the gravitational potential. And not only the number of galaxies which we see in a certain area is perturbed, but also the volume is distorted. The angles which we are looking into are not the ones into which the photons were emitted. There is lensing, there is deflection. For small catalogs, all these effects are not very important, but when we go to redshifts of order unity and more, they become very relevant. Already for the small one, the picture which we have seen before, which goes out to redshifts of 0.15 or so, or the main catalog which goes out to 0.2, or both which goes to 0.6, these effects are really important and have to be taken into account, and of course much more so for future surveys like this, Beatles and YouTube. As you all know, in a Friedmann universe, the radial distance is given by the integral of the inverse Hubble parameter over redshift, and the value of this Hubble parameter depends on the content of the universe. So in cosmology, the moment we infer a distance, we have to calculate it, and the result depends on cosmological parameters. So a K value for the power spectrum depends on the cosmological model which we use to get that K value. Depending on what we are looking at, we measure directly R of C, or we measure the angular, the area distance, or the luminosity distance to a given redshift. At small redshifts, all these distances are just given by C over H naught, and the uncertainty of and the distance uncertainty is absorbed in the fact that H naught inverse, with which we decorate all our distances in cosmology. But when we go to redshifts of order unity, the corrections to this expression become, of course, very big, and it is no longer sufficient to just take into account this uncertainty. The distance depends strongly on curvature and on lambda, etc. So if we then afterwards use, for example, a power spectrum, matter power spectrum to measure cosmological parameters, this is in principle an inconsistent thing, because we have already used cosmological parameters to get it. So it is, of course, one can then bootstrap, and that's what people usually do. One takes some set of cosmological parameters, calculates the power spectrum, sees what set of cosmological parameters one infers from that, and corrects, and this process usually will converge, but it is certainly difficult to estimate errors in such a way. Therefore, I think it is interesting to see what, to express the fluctuations in the matter distribution in terms of quantities which we really measure. And I'll follow the papers which I've done this a couple of years ago, Kami and I, and also Charlie and Louis, and there were earlier works on the same topic by Durrer. What we really measure when we build up a galaxy catalog is redshifts and two angles, so a direction vector and a redshift and some other information depending on what one is interested. And one can then count galaxies inside a redshift bin and in a small solid angle, and this gives us a number n of capital N, which depends on direction and redshift, and we can look at the fluctuations of these numbers. And we can look at the correlation function of the fluctuation of these numbers. This is a correlation function which depends on the angle between the two directions and not two redshifts. This quantity is directly measurable and therefore gauging value. And as Kami has pointed out yesterday, if you express it in linear perturbation theory, that's the expression which you obtain, where these phi and psi are the Bardeen potentials, v is the velocity in longitudinal gauge, and this ds is the density fluctuation in longitudinal gauge as well. The quantities which have been known along before was, of course, the density fluctuation, the redshift space distortion, and the lensing term. These were the quantities. This is a correction to the redshift space distortion, or the Doppler term. The These were the quantities which were discussed also yesterday in Tavistock, and there are other quantities which come from the gravitational potential and which are purely relativistic effects and which are small. Redshift space distortions have been studied and are well known, and you see, as Davi also pointed out yesterday, they are symmetrical from the back. So here you see the redshift space distortion from the Boss survey. There you see there is a flattening on large scales, and there are these fingers of code on small scales. I'm not going into this. We have already discussed that during this conference. Is it not possible to reach online?
They seem to have
It's ranging from dark. Okay, so we have these density fluctuations, which is a function of angle and redshift. So we can expand it in spherical harmonics, and we can compute the angular power spectrum, which is now a function of two redshifts, of course. Or we can calculate the angular correlation. And the relation is like in the case of the CME. Here we have some figures of the angular correlation function. Here you see the acoustic peak, which is really prominent if you multiply the angular correlation function with theta squared. So you see it really well. And if you now want to convert that into a function of distance, then this distance, of course, depends on what, for example, omega matter is. Here we took a lambda CDM with different values of omega matter. You get, of course, a different distance. And at this redshift of 0.7, this is very relevant. And if you now take this correlation function and compute the power spectrum from it, you get different power spectra for different assumptions about what the underlying matter density is. So you cannot use this to measure the power, to measure the matter density, because you have to assume a matter density to produce this figure. However, if you take just the transverse power spectrum here at C equals C prime for different redshifts, you don't need any underlying, any assumptions about the underlying cosmology. The only thing is, which you assume, is that you could work within linear perturbation theory to obtain this figure. If you look at what different contributions are to this figure, you see that the density part is the dominant contribution, but also the correlation between density and redshift space distortion cannot be neglected on a 10% level. And then there are the lensing term here in this case is very small. This is at small redshift here. Redshift constant, so the lensing term is very small. The gravitational potential terms are even smaller. The lensing term is negative because it is dominated by its by the correlation with the density term, which is negative. And you see, it looks for redshifts of 0.1. If you are happy with 10% accuracy, you can leave the density term on. But if you want better accuracy, you have to take at least redshift basis. At high redshifts, this is very different. I only show you one other result, which is assuming if you go out, if you look at the quantities at redshift 3, and you assume a really large window function, namely, you see, if you compute VCLs at a given redshift, you of course always have to take the redshift slice with a given thickness. And things depend very strongly on this thickness. If you choose a relatively thick slice, then the redshift space distortions wash out. And density goes down a lot too, but lensing does not, because lensing is an integrated effect, so it is it survives even if you have relatively thick slices. It doesn't wash out. And so you see here in this example that the lensing even dominates on large scales up to L of about 40, and is anyway very important all the way. It is like still at least half the signal at L equals 100. Now, the full information is of course not only in slices, CLs at given slices, you also have to look at the radial correlations, they are important as well. And here you see again values for, so for L equals 20, you see a first redshift which is 0.1, 0.51, 3, and then a function as a function of the second redshift. This is the density and redshift space distortion term, which passes through 0 at some redshift difference here of 0.01 roughly, and becomes negative. And if you go to higher redshifts, you see, for example, the lensing here is hardly visible, and here it comes up a little bit, but negative. And it becomes dominant at large redshift distance, but still negative if the redshift is small, and positive at large redshift. If it is positive, this means that the lensing term is dominated by the lensing contribution. When it's negative, it's dominated by the lensing density contribution, because lensing density correlation is negative. So you see, if you measure this power spectrum at redshifts 2 or 3, this radial CL power spectrum, you absolutely have to take into account lensing, otherwise you get completely. The other contributions from the gravitational potential, is a relativistic contribution, seem to be small all the way in this power spectrum. And you need some very specific way if you want to discover something. Now let us come to some real experiments. In real experiments, there is always noise. You have a finite number of one of the noise characteristics which is always there, which you cannot get rid of with the finest technology, is that the number of galaxies which you observe is finite. And here I concentrate on that noise because you see this power spectrum which we are looking at, which is a function of 3 variables, L, C, and C prime, is of course a much more noisy function than the power spectrum P of k, which is just a function of 1 variable. It's much more noisy because you have to explore a much bigger space of variables. You have 3 variables now, not only 1. So, how bad is this noise? This depends, of course, how many galaxies you have in your catalog, and then and depends on the thickness of your redshift slice. The thicker your redshift slice, the more galaxies in it, the less serious the shot noise from the galaxies. But on the other hand, the more you damp your signal, as we have seen before. So, therefore, interestingly, if you estimate this very, very crudely by hand, you find that the signal should go down like 1 over delta C, while the number of galaxies goes up like 1 over like delta C, and therefore the result should be kind of independent. And this seems to be verified. We have included the calculation of this angular power spectrum in the class code of Julia Lestur in this paper. You can download it if you want from this website and play around with it. And here you see we have looked at different thickness, redshift thickness from 0.1 down to 0.003. And we have plotted here the CL signal from if you have the thickest slice, the signal goes down most, and the signal becomes very small, but also the shock noise, which is here the dashed line, becomes very small. If your redshift thickness is, if your redshift line becomes very, very slim, then your signal goes up a lot, but also the noise goes up. And you can kind of optimize, but you see it's nearly independent around 400 or 500 where these two curves cross. Nearly independent of the thickness of your slice. So you will have to see which signal can your instrument still detect. And what are the other characteristics of your instrument which will tell you which signal you can detect. So it's kind of the shock noise which you get is nearly independent of the relative shock noise, or where the shock noise is going to overtake your signal is nearly independent of the thickness of your redshift slice. Let us consider Euclid, the kind of most ambitious project which is presently, let's say, really planned. It will measure 10 to the 7 redshifts and 10 to the 9 photosees. So there the redshift slices will be relatively thick by definition because the photosees are not very accurate, whereas with spectroscopic redshifts are much more accurate. You can have much thinner and much more slices there. Here you see the planned redshift distribution of the Euclid galaxies. If we are choosing, if we are looking at the photometric survey, we have to do Gaussian redshift bins because we cannot do top hat. The redshifts are not accurately sufficiently well known that we could do a top hat window functions for the redshifts. And here we plot the figure of merit for the measurement of the dark matter density and the Hubble parameter as a function of the number of bins which you choose. And overplotted, we have the result from a standard power spectrum analysis. That's this figure of merit. And in red are the analysis where you only take into account the autocorrelation of bins, so not the radial correlations, and in blue are those which take also into account the cross correlations. So the first thing to see is that at least in this kind of photometric redshift, cross correlations are very important, and also in the spectroscopic redshift, if you go to sufficiently very high number of bins, cross correlations become very important. Here, the lensing signal is extremely important in this catalog. When you have photometric redshifts, when you have relatively large redshift bins, and therefore including cross correlations is very important. And you see, if you include them already from 4 bins, the analysis, the radial analysis for photometric redshift is superior to the P of K analysis. Because the P of K analysis, then you don't distinguish between kind of horizontal and radial scales, and therefore you can only take into account scales which you can resolve, but if you have photometric redshifts, this goes down only to relatively large scales. And therefore this number here, even though you have much more galaxies, you have 100 times more galaxies from which our radial angular power spectrum method can really profit, the P of K method does not improve its figure of merit very much with respect to the spectroscopic one. Here, for the spectroscopic one, you see this number is still rising a lot, and here you cannot take really more bins because that's the bins which you can take into account. And even if you take 8 bins, you have a considerable overlap in the Euclid survey. However, if you would do spectroscopic redshifts, you could very easily take like 100 pins. The problem is that the computational effort goes like the number of pins squared. So if you want to do a parameter search, and if you run, let's say if you have one run to compute the power spectrum, which takes you roughly 3 seconds, which is what we have. Now, if you want to do 100 pins, these would be 10 to the 4 times 3 seconds for one run. And then if you want to do a parameter search, you have to run like a chain with 10 to the 5 runs. So this is not very realistic right now to do 100 pins, but actually this will be not probably possible. Okay. Let's see whether one can see which parts of the power spectrum one can really see in the data. For these features, look at the signal to noise from Euclid by taking into account only shot noise. At different redshifts, different redshift thickness, here the signal to noise from an individual L multipole, so to see whether one can measure this individual multipole, or maybe the signal to noise is opposed to one taking a few multiples in that state. And here the integrated signal to noise, if one goes to this L max indicated here, you see at low redshift, or at redshift 1 with a thickness of 0.1, we can this is the red curve is the redshift space distortion, the black curve is the total, the magenta one is the lensing, and the blue is the potential. So you see one can just measure the potential by adding up all the data at redshift 1. Whereas if you go from redshift 0.1 to 2.5, so up to the maximal redshift, the result is more or less dominated by lensing after. Here you see the dominant term is still the density, because it's the black curve is higher than the magenta one, significantly higher. And the magenta signal actually is negative. And then at higher L's, the magenta signal dominates the result. And here you see in the integrated or summed up signal to noise, the lensing term is the dominant one. And redshift space distortions are hardly measurable because we have such a wide redshift field, we are completely sphere out. But the potential term is not, doesn't lead to a signal to noise of one in any of these studies, so it seems not to be measurable in this way. One thing one can do is an Alport-Baczynski test. If you look at the acoustic oscillation in the radial direction and in the horizontal direction, then you have, by measuring the angle of the acoustic oscillation, you measure the acoustic oscillation scale divided by the area distance. By measuring the redshift distance in the radial acoustic oscillation, you measure the scale of the acoustic oscillation times the Hubble parameter. And if you look at the ratio L drops out, and you measure this kind of Alport-Baczynski function. And if you do that with Euclid-like survey, you will be able to measure each very high precision out to redshift 1.5. This is just fantasy, so something which would go beyond Euclid. Here, the error is dominated by the angular resolution of the survey, and we have computed it for the linear power spectrum, or in violet, or for a power spectrum where you have narrow bit corrections, nonlinear corrections, just to see how sensitive it is to nonlinearities, and it seems not to be very sensitive. Let us now come to second order number cards. These number cards which I have presented to calculate the number of galaxies have only gone to first order. But when going to second order, when we calculate them to second order, we can go further and measure, for example, a contribution to the Weiss vector, which absolutely has to be there, even if inflation is cost reduction, because just gravity is not linear. Expressing the full second order number counts in longitudinal gauge is a very cumbersome expression and not very illuminating. It would fill several transparencies here, so I spare you that one. It has been calculated by 3 groups during these years. The first calculation has been done by our chairman with 2 collaborators, Daniele Bertacci and Chris Clarkson. There have written 2 papers on this topic. There has been another paper by Johan Salvariaga, came out in June. And recently there was another paper by Enea, Giovanni Marozzi, Montanari and myself. Ours was the last one, and it's a little bit my fault that I wanted to sit on it and really make sure that everything is correct. But honestly, I don't know whether these papers, whether the expressions agree. They are so awful, and this is still work in progress, and we are not done yet with this. But let me tell you just in one transparency, in one slide, what we have done. There is a so-called geodesic right cone gauge, which has been used quite a bit by Giovanni Marozzi, Gabriele Veneziano, and Giuseppe Panizzi to calculate things which can be really useful. Here the metric takes this form. You have 2 angular coordinates, theta, which are just the angle at the observer. You have a light cone coordinate, which moves along light cone, the past light cone, and you have the time of a geodesic observer, which you call equal. That's the coordinate system which you use. For example, in the unperturbed three-point universe, tau is just cosmic time, W is the sum of conformal time and radial distance, and the θ's are just the usual polar angles. And of course, this function, this vector u vanishes, and epsilon is just the scale factor. In this, the advantage of these coordinates is that both redshift and volume perturbations in this gauge are very simple to compute exactly. The redshift of the source is just given by the ratio of the rise of the geodesic time at the observer divided by the geodesic time at the source on the same light cone. So W is the same. And the volume, if we define the volume like that, we say, okay, the volume seen by an observer moving with form velocity u is, I want to express this as some density times the measurable quantities, which are the measure of the dc and d theta d phi, the observer angles. And since in this metric, these θ's are already the angles at the observer, this just becomes, there is a small calculation which shows you that this just becomes square root of gamma, this metric here, times this ratio. So, in the geodesic light cone gauge, these 2 quantities, the volume perturbation and the redshift perturbations, are easy to compute because we can compute them exactly. But what is difficult is to translate them then in longitudinal gauge or so, and express these things in terms of the body potentials. Here I just show you the leading terms. You see already those are truly awful. Maybe some things which the leading terms are those which are second order, which are second order, but have a factor k then they are always the largest terms as long as you are on subhorizon scales. And I will show you some figures now for the bispectrum, which involve the redshift phase distortion, the lensing term coupled to the density term, and the second order density term. Here we just took the Newtonian second order density term. There are also second order velocity, second order lensing. There are lots of terms which come from the fact that if you go to second order, you have to take into account that the photon geodesic is not just a straight line, but it's perturbed, etc., etc. Anyway, you can now go and calculate the bispectrum. Even if the linear delta is Gaussian, the second order delta is no longer Gaussian, and it must link with three-point function, the non-vanishing three-point function. And this three-point function, its power spectrum, depends on 3 redshift, 3L, 3Ms, can be expressed in terms of the bond factor by spherical symmetry times some bispectrum, which depends only on the L's. And here you see some preliminary figures of these bispectrum. Here we took the second order density times first order density times first order density, and here we took velocity density correlation times density density, and you see they are roughly of the same order of magnitude. The lensing signal is much smaller. However, if we go to here we have 3 times the same redshift. If we take one redshift which is much smaller, the density signal increases, and actually the lensing signal increases, and actually the density signal goes down. But I don't show you this curve. We don't have to make this. Here you can see it as a function of redshift. Again, you see the density and redshift space distortion signals are peak, of course, at equal redshift, while the lensing signal peaks at another large redshift difference. And so that will be the way to measure this. And actually this lensing, here you see an integrated bispectrum from a minimum to a maximum redshift. And also here, in this case, the lensing signal is smaller than the other two, even though not so much. So it has to be taken into account when you want to measure this quantity, because what you measure, of course, will be the sum of it all. So let me conclude. There is this bispectrum part, as you have seen, is still preliminary. There is still a lot of work to be done there. But I think what I want to convey here is that large-scale structure data determine should that okay, so far for large-scale structure data one has mainly looked at the correlation function, power spectrum, or bispectrum as function of K. These are less noisy because they depend on less parameters, they happen on less variables. Here you just take it. This is not 9 variables but only 3, because these K1, K2, K3 have to form a triangle for the Q not to be 0 for statistical homogeneity in isotropy. But they require fiducial input cosmology to convert redshifts and angles into a length scale. This complicates parameter estimation. You probably can relatively easily get the best fit parameter, but it's very difficult to find out what your errors are. And it's not so easy to include the lensing into this bispectrum. For sufficiently large and precise 3D galaxy catalogs like Euclid, we will be able to measure the angular correlation function and power spectrum and the angular bispectrum from the data. Some precision which we are still working on to get it precisely. These quantities will be more noisy, but they also contain more information. interesting. The spectra are not only sensitive to the matter distribution, so to the density, but also to redshift space distortions and to lensing. The spectra and the bispectrum depend on several different ways, on dark energy, on the growth factor, on the distance redshift relation, etc., etc. And their measurement will provide, I think, a new and very promising route to cosmological parameter and to test general relativity. Thank you.
Thanks, Ruth, and apologies for the failure of the lights. Still down with that. Any questions?
Okay, so you mentioned for example, you use photometric redshift to give you much more information, and actually that's already the photometric redshift survey. How important it is in your analysis to know the underlying true redshift distribution? Because you assume Gaussian distribution, but in reality they are usually not Gaussian, and also you normally need some kind of training or calibration sample, which is always difficult to get. How important that will be?
Of course, if one could do more, redshift pins, the signal to noise would increase. You see it here, right? It's still, it's of course completely, very much increasing if we have more redshift pins. So here we took Gaussian pins with, which have a width, which is the one which is given in the red book, and we took this distribution. We could nowhere find, for example, the photometric redshift distribution for you know, only the spectroscopic one, so we assumed it to be the same. It may very well not be. It doesn't depend so much on whether this redshift distribution is Gaussian or something else. We made some tests. It's not very sensitive to that. It's only very sensitive to the number of pins and the number of galaxies per pins. Of course, it's very sensitive on whether you tell me you're going only to redshift 1.2 or you're going to redshift 3. This is very important to know. And to know roughly how many galaxies here, for example, you see this last pin is very large because we found that we get the optimal figure of merit if we choose the same number of galaxies per pin. So here, since the galaxy number density goes down, we choose a larger pin, the last one, and this pin in the center is quite a bit smaller. But if we could increase the number of pins, you see here, I don't quite exactly know what the slope is, but you see it goes up a lot. If you double the number of pins, you go from 140 to 120, so you see what roughly the slope is.
Any other questions? I have a question, Ruth. In your plots where you show the lensing and the potential and the redshift space distortion, what about the Doppler terms? Were they? Some of them I thought there was only those two. I mean, in the later plots.
Here they are.
Okay, but then later on.
And later on in this, where I show the signal to noise, they are included in there. They are included in the here. They are included in the Doppler term. So, sorry, in the redshift space is Doppler term. So I can't tell you, but my guess is that they are not much bigger than that they are roughly the same as the. But I don't show them the same.
And the phi term, which is the redshift space term, did you put that in the potentials or in the redshift distribution?
In the potentials. Yeah.
I suppose this is part of the game to think split these things.
You can, you know, the step between the two, you can make, you can use or not use the Euler equation to get rid of the radial derivative of the potential. And I use
clarity in your non-linear formula in the eye spectra, this is on quasi-linear scale. It's not down to halo.
Absolutely, of course. I mean, that bispectrum is second-order perturbation theory. So if things are non-perturbative, this second-order perturbation theory is no good.
Right, well, let's thank Ruth again, and we'll reconvene. That's 11:15 for the last one.
No, I'm going there. Why don't you... Carta.